Today we're talking about accuracy, precision, and error. Our first essential question today is how are accuracy and precision similar and different? This essential question should be at the top of your notes. We're going to start with some definitions. A lot of people use accuracy and precision, or accurate and precise, interchangeably, but in reality the definitions are different and the two words mean different things. Accuracy is how correct you are, how close your measurement comes to the real and correct answer. Precision is how close a series of measurements are to each other, and that one doesn't matter on the actual value. So you can be precise and be totally inaccurate. We'll see a couple of examples of this, but for right now, get down the definitions. It's best if you put them in your own words. When we evaluate accuracy, it's important that we compare the value that we've measured to the correct answer. So for accuracy, we're comparing to the correct value. For precision, let me just change colors here real quick. For precision, to evaluate precision, for precision, well, it's not a great color, but whatever, you get it. For precision, we want to look at, compare the values of two or more repeated measurements. So for precision, we want to compare a series of measurements. I abbreviate measurement MMT. You can abbreviate it however you like, or not abbreviate it at all. But we're looking for a series of measurements with precision. All right. Here's some examples. For accuracy, we need one bullseye. Here we have 3 bullseyes, which means we have good accuracy and good precision. If I have three darts that hit all in the same area, but are not near the bullseye, I've got good precision, but poor accuracy. To be accurate, you only need one measurement, or one arrow, and that arrow can be right at the center. So now that I've put an extra arrow in there, wow, this is pretty pathetic, to be honest with you. I don't have good drawing skills, but anyway, you see that I have one measurement with good accuracy. The rest have poor accuracy, but the rest are good on precision because they're all close together. Our last example here, I've got stuff all over the place, none of which have hit the bullseye. Here I have 0 accuracy and 0 precision. If, on the other hand, I had a bullseye, forgive my drawing skills, we all know they suck. Alright, so here's my bullseye. Okay. Oh, geez. Alright, so here's my bullseye. If instead I had, let me change colors. If I had a mark here, one here, another one here, I am no good with this. One day I'll figure it out. I don't know how to make it just right. And one here. So now I have okay accuracy. All of my marks are close to the bullseye. They don't necessarily have to be perfect on the bullseye, but they're all kind of close to the bullseye. So my accuracy is okay. Okay accuracy. My precision sucks though, because none of them are close to each other. So I have bad. Oh my goodness. Oh my nerves. Bad precision. Okay, forget it. Alright, I don't know what just happened. Let's go back. There we go. Bad precision. Let me get that ink pen again. Bad precision. Okay, so I've got okay accuracy here, but I definitely have poor precision. Alright, let's move on from accuracy and precision and talk about error. Let's say we're using a thermometer and we want to measure the boiling point of pure water, H2O, not tap water, but distilled water, H2O. You know that the boiling point of water is 100 degrees Celsius. You know that, you've been exposed to that many, many times. If you've forgotten, now you remember the boiling point of water is 100 degrees Celsius. If the thermometer tells me that the boiling point of my water is 99.1 degrees Celsius, there is an error. Error means it's wrong. So the thermometer is wrong. In this instance, the error is off by a systematic error. So a systematic error is something that we can fix using math. So a systematic error is any error that we can fix using math. Oops, that's not what I want. Fix using math. So systematic error, any error we can fix using math. This thermometer is off, and every time it measures, it will be off by the same amount. So it has a systematic error. What I want to know is, what's my percent error? So to find percent error, we need to figure out our error, our raw error, and to do that, we need this formula here. So in your notebook, in your notes, make sure you have the formula for error. The experimental value is the one that we have measured. We've measured this. And the accepted value is the quote-unquote correct. This is the correct or right answer. So this is always given to you. That's really important to remember. This will always be given to you. In the problem, in the lab write-up, somehow this value will be told to you. So to find our error, we take the measured value and subtract the correct value. Well, what's that for our water? We measured our water at 99.1 degrees Celsius, and the correct value is 100.0 degrees Celsius. So when we subtract those two, our error is 0.9 degrees Celsius. 0.9 degrees Celsius. Oops, that should be a negative. Negative 0.9 degrees Celsius. So our error is off. This tells us how far off we are. It can be positive, it can be negative. It doesn't matter. I want to take this now and find out how far off I am compared to my accepted value. That's called the percent error. The percent error is a measure of the absolute value of the error, and it's easier to compare. So make sure that you have this formula for percent error in your notes, but I'm going to take this top one, cross that out, and put in my formula for error itself. So we need the absolute value of the measured minus the accepted. The absolute value of measured minus the accepted divided by the accepted value multiplied by 100%. Do not use the percent symbol on your calculator, otherwise that's going to give you some funky answer. So we'll do a couple of problems with this today. But do make sure that you have this formula in your notes. Okay, so let's calculate the percent error of our boiling point problem. I've got this thermometer that's registering 99.1 degrees Celsius. We know that's wrong. We know the correct value is 100 degrees Celsius, or 100.0 degrees Celsius, if I use my correct number of significant figures. And so what I want to do is figure out how far off I am. What percent am I off? So on the top, let's see. So this is what I know, blah, blah, blah. All right, here we go. We've got our formula. We're going to replace this with the absolute value of the measured minus accepted. And now we can plug things in. So our percent error is on top. I have my measured value. That was 99.1 degrees Celsius. Minus my accepted value 100.0 degrees Celsius. I need to take the absolute value of that and divide it by my accepted value, which is 100.0 degrees Celsius. Take the answer of that and multiply by 100%. The units on this is percent. I'm going to put that in a different color because that's pretty important. The units are percent. Percent is your units here, not degrees Celsius. Anytime you're doing a percent error or a percent composition or anything with percent, the unit is percent. So that's an important thing to know. Sorry, I just crossed through the percent. The units are percent. All right, let's do some math. Oh, I lost my cursor. Let's do some math. So for my percent error, 99.1 minus 100 will give me negative 0.9 degrees Celsius divided by 100.0 degrees Celsius times 100%. So that's the same thing as saying 0.9 degrees Celsius over 100.0 degrees Celsius times 100%. For those math majors in the room, my math whizzes, you see that I can cancel out the 100 here. If there's something on top and something on bottom, you can cancel it out. I can also cancel out these units, the degrees C and degrees C, those can cancel out. So my final answer comes out to 0.9%. If we take a look at significant figures, let's look at significant figures because we've, have we learned that yet? No, I don't think we have. Never mind, we can ignore significant figures for now. We'll come back to that when we know sig figs. But for now, our answer, what's the percent error in this problem? 0.9%. And here's another version of that, basically the same thing that we just did, all written out, but 0.9% is our answer. And the question is, does this really make sense? Every time you do a problem, you want to take a look at your answer and say, does this make sense? And yeah, it does. Our answer was off by almost 1 degree. And that's 1/100th of the accepted value, so it's about 1%, and that does make sense. I've got another question for you. I want to know if precise measurements are always accurate. So we'll have a quick class discussion about that. Are precise measurements always accurate? I also want to know, after we've discussed that, let's see, let's get a reasonable color. After we've discussed that, I want to know, are accurate measurements always precise? Okay, so those are two questions that we'll discuss as a class. Yeah, that's all.